Okay, moving right along. We are on problem 7, where we got these two blocks that you can't see because of the weird graphics thing. I'm not sure why the cutting and pasting doesn't work for these, but whatever. So you got these two blocks, M1 and M2. There's M2 and there's M1, close enough. And we have to, they're on a frictionless surface. We're given an angle, I'm going to call it theta because I think it varies per problem or per person. It's 30 degrees for everyone, so fine, we'll just make it, well, whatever, we'll say it's theta. And you have to find the acceleration of the blocks, let's see, find the acceleration of the blocks, direction and tension, direction and tension. Okay, good enough. So this is not very hard. So let's identify. So I'm going to draw my little sketch of block 1. There's M1 on this slope, which has an angle of theta. And so what are our forces acting on block 1? Of course, we've got gravity, good old M1G down there. We've got our normal force, good old N1, I'll call it. And we got the tension. Friction force? Nope, because we don't have friction here. So, and block 1 we're going to say is accelerating. We're just going to define this as being up. So I'm going to say acceleration is in positive x because I'm going to define positive x going that way and positive y going up. So let's do our FBD for block 1, and we can do this, right? We do a little x, y, and there's our dot, and we got our, this is a little crowded, so apologies for that, but there's our tension, and there's our weight, M1G, and that angle, the angle between the weight and the y-axis, is theta. So let's see if I can do something a little less fugly here for this one. And there's N1, there's T, there is our mg sine theta going that way, and down here we have our mg cosine theta. Well, normal force and mg cosine theta act in the y direction, and gosh, that's sure nice for them, but I don't think we actually care. I think we can do this by just doing an x force balance. So let's try that. Sum of forces in the x direction is of course going to equal the mass of block 1 times block 1's acceleration, which we've decided is we're going to call a, and that's going in the positive x direction, so we just plug that right in. Okay, so let's say t, that's going in the positive x direction, minus mg sine theta, and that's m1g, so let's watch out for that, equals m1a. So let's see, what do we want to find? Find a first. Let's solve this for a. A equals t over m1, we're just dividing through by m1, minus g sine theta. Well, that couldn't be simpler. So now we need to do it for 2 so we can get rid of these t's in our answer, or t's in our, yeah. So let's see, FBD for 2. So let's see, here's block 2, it's just sitting there. Well, actually, that's not an FBD, so I'm just going to, I'll draw a little sketch of block 2 here. Okay, so there's block 2, M2, and what are the forces acting on block 2? Well, everything's got weight, and then the cord is pulling up on it. So here's block 2, weight coming down, cord pulling up. What's left? Well, that's pretty much it, actually. So let's go do our FBD for block 2. I'm going to say positive y going down here, just to be contrarian. Actually, because I know that, here's the thing, if block 1 accelerates uphill, then it's coming closer to the pulley, which means block 2 has to be accelerating downhill, coming further from the pulley, right? So I'm going to say this A here is block 2, and it's the same A as this one, because if block 1 is accelerating up the hill, block 2 has to be accelerating straight down. And that's why I put my positive y like that. So let's do our free body diagram. And remember, you can define different axes for different parts of your problem. So up here, you know, here's my x and my y. Over here, there's my y going down and my x going sideways. This is for block 2, and this is for block 1. Completely different, but it doesn't matter because we don't. There's no reason these need to be the same. All that they're connected by is the pulley, or is the string going over the pulley, and that's just got the tension, and they've got the same acceleration. But that's, as long as we're accounting for that, it doesn't matter that we use different axes. So for the free body diagram for number 2, there's our tension. I'm going to draw my coordinate axes because, you know, I'm a good physicist. And there's my M2G. And so let's do a sum of forces in the y direction. Now remember, I defined y positive going down. So I'm going to say, well, and this is going to equal M2 times A, where A is going down. Y positive, positive, okay. So this is going to be M2G minus T. So we got the down being positive, up being negative, equals M2A. And then we can say, well, what the hell? Let's go ahead and solve this for A. A equals, so we're going to divide through by M2 here, and it's going to equal G minus T over M2. Easy enough. Now you take these two equations, and actually I'm going to get a new color. Let's get this sort of cobalt blue thing. That's not bad. And get these two equations and put them together. So this A and this A, we're going to set them equal. And what that's going to give us is G minus T over M2 equals T over M1 minus G sine theta. Okay, well, I'm going to scroll us down a wee tad. And let's just multiply through, let's see, what should we do? Oh, let's just multiply through everything by, oh, I don't know. I don't know what to do here. This is annoying. So let's collect all the t's on one side. So let's do negative t over m1 minus t over m2 equals negative g sine theta minus g. Okay, well actually we can, everything's negative here, so we can just make these all positive. Boom, 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 boom. And then we get, you know, I don't know how we want to do this. Let's see. I guess if we want to add these together, we have to get these two the same denominator. So that's going to give us like m2t plus m1t over m1 m2. That's the left-hand side equals, and then this is going to be g times 1 plus sine theta. And then, wait a minute. No, we were supposed to find the acceleration. Oh my god, unbelievable. Okay, well, I've just basically sort of gone about this back-asswards. But, nah, what the hell, you only live once. So, this gets our tension, and then our, this here, actually, let me switch colors yet again. So this here, then, is going to simplify out to t times m1 plus m2 over m1 m2 equals g. No, this can't be right because I've got, what have I done wrong? No, I'm good. Never mind. Equals g times 1 plus sine theta. So you know what? I'm feeling just weird enough about this. So I've got tension here. I know m1 and m2 and g. So I'm going to go ahead and calculate this out because I am feeling kind of a little skittish about this. So let's see. T times m1 plus m2 over m1 m2. So let's see. We have our previewer. Okay, 3.10. So wait a minute. No, that's not. Oh yeah, so right. I'm sorry. So this. Wow, you caught me on like the worst day here. Okay, t equals g times 1 plus sine theta. Actually, hold on. Let's. All right. T equals 1 plus sine theta g times m1 m2 over m1 plus m2. All right, this is horrible, but let's see what I can do here with this. So let's get our calculator, and let's see. And actually, I'm gonna close some of that and something like that. All right. So here's our calculator. Let's see, 1 plus sine theta, so 1 plus sine 30. Okay, and we're going to do all that. 9.8 times, and then this is going to be, what are these two masses again? 4.1 and 2.5. Okay, 4.1 times 2.5 divided by, and then 4.1 plus 2.5. All right, so and that was right. That's what it's supposed to be. Okay, so let's see how this goes. 22.99 is our tension in the cord. So let's just see. 22. Actually, well, I'm giving the answers here because I'm special. So actually, I did get that correct, unbelievably. Okay, so anyway, now that we've done all that, let's see if we can come up with something slightly less painful for A, although probably not. So let's switch to, I don't know, let's say brown here. And we're going to take this equation here, which looks simple enough. So, and we're going to plug in this t. So A equals G minus t divided by m2. Oh boy. So that's actually just this 1 plus sine theta times g, and then dividing by m2. So we can cancel out our m2 there. And so if we take this equation and this equation, plug t in, then this is what we get. And then I guess we can do like a blah, 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 blah. Let's see. So we can make this like gm1 plus gm2 over m1 plus m2. That's just this g here. Minus, and then we did, this will be gm1 plus gm1 sine theta over m1 plus m2. So then we just take this and this gm1 and this gm1 cancel out. So really, acceleration is going to equal g times m2 minus, so we're going to minus in this term here, minus m1 sine theta over m1 plus m2. I think that looks correct to me, but just for the hell of it, I'm gonna do it again with the calculator, since we've already gone this far, and I don't know. Oh man, I'm just rambling now. All right, so let's do 9.81 times, and m2 I think was the 2.1, but let's check it. So m2 is 2.5 and m1 is the 4.1, right? So 2.5 minus 4.1 times sine 30 times, or divided by 2.5 plus 4.1, and then 0.669 is the magnitude of our acceleration. And yep, okay, so I got that right. And then which one accelerates which way? Well, we defined here, we got a positive number, 0.669, and here we define positive as being m going uphill and a going down. And so you can see here clearly that m2 goes down. So that was correct. Wow. So, longest solution for simple problem ever. But there you go.